Hello out there, everyone. Welcome back to class. I'm Dr. Dax, and this is week 3, session 2 of your infrastructure hardware course. I hope everybody out there is doing well this week, that you've had a great week so far, and that you're geared up and excited about the weekend, and excited about proceeding on to Deliverable 3, which is what we're going to be doing today. But before we get into that, we're going to cover some content, some more material that will help you develop a good working vocabulary to build that report for Deliverable 3. Before we do that, though, let me see if anybody else is coming in. They are not. All right. So if you are in a part of the country where it's hotter than Hades, like it is here, forgive me for sweating. Our air conditioning is out. And so we're having a lot of fun. Good times, good times. First world problems. But I've got a repair guy coming to take care of things soon, hopefully. But in the meantime, we'll just keep on trucking. We're good to go. We're good. So sit back, relax, grab a favorite beverage, and let's get this show on the road. So we've been talking about intelligent systems and what that means in the space of creating data center materials, and that's going to speak into our third deliverable. First, what we'll do is we'll get a review going from our first week, from our first discussion this week on intelligent storage systems. Then we'll build on that. Our objectives for today are: after you're completing this session, you should be able to describe components of intelligent storage systems, list the benefits of an intelligent storage system, explain intelligent cache algorithms and protection, and describe intelligent storage array implementation to include high-end storage arrays, mid-range storage array. So before we get too deep down the rabbit hole, let's take a review of what we talked about on Tuesday. We won't spend a whole lot of time here, but I wanted to hit some concepts because we're going to build on those for today's talk. And then at the end of that, we will describe the expectations for deliverable 3. And as always, if you guys have any questions after the session, if you just reach out to me with your question, I will respond to you within 24 hours. You can call or text or send me an email. All the contact info is on the main page. And let's get the show on the road. So, intelligent storage systems are RAID arrays that we described previously, and they highly optimize I/O processing, inputs and outputs, and they have large amounts of cache memory for improved I/O performance. It prevents buffering and runs a lot more smoothly these days. And they have operating environments that provide intelligence for managing the cache memory and array sourced allocation. So things can be changed on the fly, locally or remotely in most cases, and it provides connectivity for heterogeneous hosts and an advanced array based local and remote replication options. There are many benefits to intelligent storage systems, benefits that include things like an intelligent storage system that can provide increased capacity, improved performance because of the fact that you have cache memory management capabilities, easier data management, and improved data availability and protection, as well as an enhanced business continuity support and improved security and access control. Recall that the components of an intelligent storage system include the host, the front end, which is comprised of the controllers and individual ports within those controllers, which attach through the FCSAN storage area network to the host. And the I/O requests come in to the front end controller, and they're processed for I/O processing and sent out to cylinders. So with command queuing, you're able to actually take the data and rearrange the processing order depending on the needs of that particular transfer. The intelligent storage system cache memory is between the front end and the back end, and it allows for some highly efficient transfers. There is a write through and write back cache memory. In the cache memory in the write through, write request is sent and then processed through the silos and back after an acknowledgement. Write back is acknowledged as soon as it enters the cache memory. It sends a write request and bounces back. Then it is acknowledged by the silos or the end RAID arrays, acknowledged and bounce back. So the read operation with cache includes hits and misses. For the data found in the cache in a hit situation, the read request is sent. There's a hit in the cache memory, acknowledgement, and it goes back to the array. For a miss, as you can see depicted here, continues on out, then is acknowledged in the RAID and bounce back. Cache management algorithms are processed here as the new data enters in and eventually becomes the oldest data. It is done on a first in, first out basis. A least recently used algorithm is which discards the least recently used data. In the MRU, the most recently used, that is where it discards the most recently used data. And intelligent systems can use watermarking. In watermarking, the idle flushing is depicted here. High watermark flushing continues up past the HWM's mark. And in forced flushing, it continues on to 100% capacity. Watermarking is flexible and can be set remotely or locally. It manages peak I/O request bursts through flushing and destaging. Idle flushing, high watermark flushing, and forced flushing are there for maximum performance, which provides headroom in write cache for I/O bursts. So in idle flushing, you got additional space left. For cache data protection, we protect the cache data against failure through cache mirroring, where each write to the cache is held in two different memory locations on two independent memory cards. Cache vaulting is where cache is exposed to a risk of uncommitted data loss due to a failure. The backend and physical disks are represented here. The controllers are pointed toward the physical disk or the array. The data is sent there. And what the host sees, the RAID sets and LUNs here. LUN masking is an access control mechanism. It's a process of masking LUNs from authorized access. So it's a form of internet security. By implementing in storage arrays, the storage group local entity that contains one or more LUNs and one host are implemented. Now, an ISS implementation for high-end storage systems, it's also referred to as active arrays. IOs are serviced through all the available paths. It's kind of almost a brute force algorithm. Following our high-end array capabilities, they include things like storage capacity, huge cache to service host IOs, fault tolerance architecture, and multiple front-end ports, and support to interface protocols. It is also highly scalable, so as the organization grows, it can grow with it to a point, and it provides the ability to handle large amounts of concurrent IOs. And it's designed mostly for large enterprises. In mid-range storage systems, they are also referred to as active-passive arrays. The host can perform IOs to LUNs only through the active path. The other path remains passive until the active fails. Mid-range arrays have two controllers, each with cache memory, RAID controllers, and disk drive interfaces. They're designed for small and medium enterprises. They are less scalable as compared to the high-end array, but for a small to mid-range company, that's not as important. So some things that we've covered so far on your refresher are about intelligent system features, components of intelligent storage systems, cache management algorithms, and intelligent storage system implementation with high-end storage array and mid-range storage array. If you want more resources on those materials, send me a message and I will provide them for you. But let's move on. Components of the storage array network, or SAN, involve three basic components. Spoiler alert, you might want to write these down. They consist of the server, the network infrastructure, and the storage. Those are the three basic core components of the SAN: server, network infrastructure, storage. Those elements are classified into the following elements, like a node port, cables, interconnection devices, storage array, and SAN management software. For the Internet Small Computer Interface, or ISCSI, the transport layer protocol that describes how a small computer system interface packets should be transported over a network like a TCP IP network. That protocol works on top of the TCP, the Transport Control Protocol. And it allows the SCSI command to be sent over the end-to-end over local area networks, or LANs, as well as wide area networks or the internet. The ISCSI works by transporting block level data between an ISCSI initiator on a server and an ISCSI target on a storage device. And the ISCSI protocol encapsulates SCSI commands and assembles the data into packets for the TCP IP layer. Packets are then sent over the network using point-to-point connections. And upon arrival, it disassembles the packets, separating the SCSI commands so that the OS, or operating system, will see the storage as if it was a locally connected SCSI device, and it can be formatted as usual. Network attached storage, or NAS devices, store and share data for multiple computers, and they can be accessed remotely. Storage-related issues include things like lower cost options, the ease of operations. Many small businesses don't have an IT staff on hand, so this is handy in case you use a third-party organization or talent from another part of the country. And there's the ease of data backup. It's always accessible, always there when you need it. Additionally, it provides growth capability. Network attached storage is extremely flexible in this area. Some of the benefits also include the fact that they're simple to operate. A dedicated IT professional is, generally speaking, not required. It doesn't require as much training as the higher end systems, and it can be handled by third-party technicians that are not super expensive. It also comes at a lower cost. It can significantly reduce wasted space or the storage systems, like the storage area network. And it provides the option for easy data backup and recovery with granular security features. And it supports a large variety of applications. Also, NAS permits data access across the network, including cloud-based applications and data. So all this comes together to help develop your data centers. Excuse me. A data center is basically a facility for housing a large amount of computer or communications equipment. Often it is both. I work in a central office environment, which is basically a souped up data center that provides services for telecom customers, as well as alarm systems and other interrelated technology. They consist of racks, power supply tools, PUEs, and cooling, as well as the containers and the economics of the situation. A data center is composed of a physically safe and secure space. It consists of racks that hold the computer, network, and storage devices, electric power sufficient to operate and install devices, and cooling to keep the devices within their operating temperature ranges, as well as network connectivity throughout the data center and to places beyond. This is a quick overview. I'm not going to read the whole material to you, but it's just a good pictorial representation of the power needs, the cooling and the UPS system, and the pump room and so forth. So this is your co-location suites. These are often caged in, and this is where the nodes for the various telecom providers exist. And you can also have your servers and your routers and switches set up. The PDU is the power distribution unit. They typically run up to 225 kilovolt amps per unit, and it provides redundancy. And I want to draw your attention to the fuel oil storage tanks. Now, they work in conjunction with the batteries in order to provide service in the event of a commercial power loss. There's an automatic switch, and these typically are really large. They're about the size of a van, maybe a little bigger. They're big generators that you might see on a farm, and they run on diesel. And typically, there are power crews that are dedicated to just monitoring their services. They do the monthly routine maintenance. They'll do an engine run. They'll actually simulate a power transfer by taking one of the three phases offline, and that basically to the computer it will look like a commercial power loss. So it kicks in, turns on the generator, and the lights will flick off and flick back on real quickly, except for systems that are connected to battery backups. And we describe racks here as basically the skeleton of the data center. There is the 19-inch rack standard, and an example is the EIA 310, and there are other standard numbers. The NEBS 21-inch racks, which is used to house telecom equipment, switches, routers, and there's 2-post or 4-post racks. They provide air circulation, usually in fans. Now, the fans typically are built into the nodes themselves, but there are some systems that don't have them internally built. You have to have an additional rack mount for the fans. And it allows room for cable management. And there are usually doors, or it may be wide open. Rack units themselves come in different sizes, and your assignment will have to deal with the benefits of the smaller rack units. And so rack units are basically listed as 1U, 2U, 3U, and they're multiples of 1.25 inches here. 1.25 inches is 1 unit. And so your rack mounts basically have the option to use the small to the large 1, 2, and 3 unit pieces. It's an industry standard in the world. Get back here. Something happened to my presentation. Let me get it back up. All right. Sorry about that. Teams had a weird glitch just in. Okay. Rack sizes. Okay, so you got the smaller rack mounts that are represented here, the 22 unit, the 36 unit are in the middle, and the 42 unit on the right. They have different benefits. Now, the smaller rack units take up less space, and they provide greater cooling possibilities for passive systems because of the greater space there that you'll have in the room. And they have the disadvantage that there's no scalability. Once you fill them up quickly and easily, you can't do much more with it. Different rack purposes are listed here. They are here for the organization of equipment. Over here, this one is the one that pulls out. You can see the OS that's there for local operation, for backups and testing. You can also organize the cables and the cable runs. I wish that the ones in my building were that neatly put together. That's a really nice install. Organized equipment. You increase the density with vertical stacking. And for cooling, there's an internal airflow because of the rack mounted fans. They pull the air through, keep the servers cool within the operating range. And the data center airflow is determined by the arrangement of the racks. So you want to ensure that there is sufficient space between the racks. And wiring organization is where the cable guides keep the cables within the racks. Usually on the sides, the vertical runs are covered with a piece of plastic that houses a not a pipe, but a square looking contraption that holds the cables, but not always. And sometimes instead of rack mounts like this, they're cable tied to the steel rack. It just depends on who installed it and what the standards were. And the rack power infrastructure, you've got power distribution units here. The PDUs are kind of like breakers. They have space for 4 sockets, and there's different power sockets that can be used for different circuits. They're individual outlets for control, and they have a current monitoring system as well as alarms that can operate locally and remotely. And they're network managed either through the web or the SNMP. Rack mount servers look kind of like this. They're 1 unit up to 4 units. And blade servers operate in a large housing here that's installed initially, usually by the contractor, and then on an individual basis, the different cards can be ordered and placed in. Now, when the cards aren't used, those slots have a blank covering them up. In buying a rack for your organization, you will want to ensure that you have the right size, something that is appropriate for the project. You want to assume that you have a certain number of servers and allow for some growth. And you want the size to allow space for power or the patch panels, and make sure that it fits the servers. And it includes the appropriate mounting rails and shelves for non-rack servers. Environmental options include the option of locking front and back doors. They're not always necessary. It depends on the facility. Excuse me, if it is a freestanding facility that's all it is the data center, generally the data center access provides the security. If this is part of a larger organization like a secondary education facility, college, or a hospital, then there will be additional safeguards. There will be sufficient power and cooling, and power and environmental monitors, and a console if needed. Sometimes they're built into the system, like the one we showed you on the previous page, but more often than not, there's a port, either a serial port, an Ethernet port, or another similar port that you can connect your computer to through a USB and talk to the system through your software. And that way you can monitor alarms, make changes in the configuration, and so forth. In the aisles, you want to make sure that there's enough space for movement in between the systems. Separate hot and cold aisles. And for hot spots, you want to avoid those because that is the result of poor airflow. You can see here in this diagram where heat escapes this side of this row of servers, and this other server is built so that the heat escapes facing it. That could create a potential hot spot, so you want to be careful about that. Servers can overheat when the average room temperature is too low. The workspace is a space for SAs to work on the servers. You want to include desk space, room for tools, and you want to avoid cluttering it and ensure that the capacity is there with room to grow. So if you're designing the initial facility, don't design it to be full right away. Allow for some scalability. And we mentioned UPS earlier, but we kind of glossed it over. UPS is your uninterrupted power supply. That means that whenever there's a commercial power loss, that battery backups kick in, and if there is a diesel generator in place, that it kicks over automatically, and consumers are none the wiser. It provides emergency power when the utility fails, Most use batteries to store power. Some use the engines that we talked about. Some have both. The offices that I work in actually have both. And the batteries are set to work for several days, but beyond that, you depend on the generators. Conditions: power, removing voltage spikes. For a standby UPS, power will be briefly interrupted during a switch, and computers may lock up or reboot during interruption. There's no power conditioning. Um, there's a short battery life, and very inexpensive. Online UPS is based on an AC to DC conversion. It's a true uninterrupted power supply without switching. It's extremely good for power conditioning, providing the ability to eliminate spikes, and it consists of longer battery life, but it comes at a much higher price. And the power distribution unit basically takes high voltage feeds and divides them into many different 120 and 110 voltage circuits that can feed servers. All right, so with that, let's go ahead and talk about Deliverable 3, your pros and cons of a smaller chassis. Now, in Deliverable 3, you're going to be asked to provide an Excel spreadsheet with a side-by-side comparison of various types of smaller chassis. Honestly, if you don't want to do it on a spreadsheet, if you can do it in your Word doc or as an image, that's fine. Just make sure you include all the information. What I don't want you to do is create a spreadsheet and then do a screenshot of that and stick it on a Word file, because that tends to bleed off of the side of the page sometimes, and for some reason I can't see all the information. You'll provide analysis of a minimum of 4 best practices for installing hardware in racks. We've talked about some of them tonight, so you can use that as a resource if you like. Provide an evaluation of a minimum of 4 core elements of physical security and controls, and a minimum of 4 best practices for installing hardware in racks. It sounds like a lot, but let's take a look at the rubric, and that'll tell you exactly what you're going to be graded on. First, criteria: a clear and concise explanation that covers the pros and cons of a smaller chassis. Here, you're going to want to be objective and provide both the advantages and the disadvantages of the smaller chassis. I touched on some of them tonight, but I didn't give you all of it. It's up to you to do your due diligence, and I encourage you to read the material for Module 3 to help you, and also draw from as many external resources as you can. Get used to the idea of doing a lot of research online and citing that material. You'll provide a full explanation of the impact of 4 or more criteria, analyzing the best practices for installing hardware in racks. So 4 or more best practices described and justified. It sounds like a lot at this point. Don't be overwhelmed. Once you get started and you understand what you're looking at, it'll almost write itself. So find those resources, and it'll help you tremendously. For explanation of 4 or more core elements involving physical security and controls for the data center. Security controls can be something as simple as simple locks on the doors, different types, bioscanners like fingerprint scanners. Other controls can be a human element, challenging someone who doesn't have an ID, physical security badges. Additionally, you can include a discussion of alarm systems and the different types of contacts for doors and windows that can be helpful. Locks on the cages that are internal in the facility. There are lots of great examples out there. And a full explanation that covers 4 core elements in creating best practices for installation hardware in racks, and some basic examples included. So the expectations are pretty simple. If you can fulfill those 4 different criteria and include lecture notes, if you're doing this on a PowerPoint presentation, put lecture notes at the bottom. Don't just do your 2 or 3 bullet points and leave it alone. Flesh it out. And provide an appropriate use of graphics. If you're using a description of a specific commercial solution, provide images of that, and cite your references. Always use citations where appropriate. Anytime you're saying something in the body of your context, if something that's not widely known, you're going to want to put a citation in the reference, not just at the reference list at the end, but in the body of the paper. Okay. And that is about it for today, guys. I hope that this has been helpful for you. If you have any questions about anything, reach out to me. You can call or text me at dax.bradley@rasmussen.edu. And you can email it. That was my email address. You can call me at 252-458-7176 or send me a text. That usually works better because my hands are full during the day, and I will get back to you within 24 hours. Just let me know what class number you're in and your question, and we'll work with you. If you need additional resources, let me know. I'm here to help you guys succeed. I want to see you guys all perform to the best of your ability. And what I've seen so far has been excellent. So keep up the great work, and let's see some more deliverables rolling in starting next week. Okay, that's it for now, guys. Thanks for watching. Dr. Dex out.